What if I told you there's a secret language that powers literally everything? I'm talking about the way you're thinking right now to the device you're watching this on. Well, it's the language of electrical signals. And over the next few minutes, we're going to dive in and decode it together. Okay, so let's start with a little riddle. What could possibly connect your brain, your own heart, and a massive industrial robot on a factory floor? I mean, they seem like they're from completely different worlds, right? But they all share a fundamental and kind of amazing secret. And the answer is, they all speak the same language, the language of electrical signals. And for us humans, it all starts right here with the neuron. These are the basic messengers in our nervous system, firing off these tiny little electrical pulses that let us think and feel and move.
And this is what that message actually looks like when it's being sent. When a neuron fires, it creates this super fast electrical spike. It's called an action potential. It's just this tiny, brief change in voltage that lasts for, milliseconds. But it's the absolute basic unit of information that's letting you process my voice right now.
These biological messages are so critical that they have their own special name, biosignals. And that just means any signal in a living thing that we can measure and watch over time. It's like a constant stream of data our bodies are producing every single second.
And we listen to these signals all the time, especially in medicine. You've heard of these, right? An EEG is listening to the electrical chatter of the brain. An ECG or EKG tracks the powerful rhythmic signal of the heart. EMG measures when your muscles fire up, and an EOG can even track your eye movements. Our bodies are just buzzing with electricity.
All right, so we know these signals are everywhere, from inside our own heads to the machines we build. But to really get a handle on how they work, whether it's a brainwave or a Wi-Fi broadcast, we need to break down the wave itself. What makes a signal a signal? So pretty much every signal has three key characteristics. First, you've got its height. That's the amplitude, and it tells you how strong or intense the signal is. Think of it like the volume on your stereo. Next step is frequency. See how close together the waves are? That's how many waves go by in 1 second. A high frequency is like a high-pitched note. And finally, the period is just the time it takes for one single wave to do its thing, to go up and down. If you get these three, you've got the building blocks to understand any signal out there. Now, signals mostly come in two main flavors. Over on the left, you've got analog. It's this smooth, flowing, continuous wave that captures all the little details of the real world, like the sound of my voice. But our computers, they don't really do smooth. They think in steps, and that's the digital signal on the right. It's the same information, but it's been chopped up and converted into a series of separate on or off values. Let's just put them right next to each other to make it super clear. An analog signal is continuous. It gets every little bit of information. A digital signal is discrete. It just takes little snapshots of the analog wave and turns them into ones and zeros. The world around us is analog, but our computers, our phones, pretty much all of our modern tech, it all speaks digital. I absolutely love this analogy. It just makes it click. So picture an old school telegraph. You tap out a message, and for each letter, you send a distinct burst of energy. That's an energy signal. It has a beginning and an end. Now think about a radio station. It's sending out a continuous wave all day, all night. That's a power signal. The music is just encoded on top of that constant wave. It's such a simple way to get the difference. Okay, so we've got the theory down. We know what signals are made of, and that they come in analog and digital flavors. But how do we actually read this language? How do we take something happening in the real world and turn it into something a computer can actually use? Really, the key question here is all about translation. How do we bridge that gap between a physical event, like a heartbeat, or the room getting warmer, or a button being pressed, and turn it into clean, useful digital data? Well, this whole journey is called data acquisition. It all starts with a sensor, or a transducer, which takes that physical thing and turns it into a raw and usually pretty messy electrical signal. Then that signal has to go through conditioning. This is like the cleanup crew. It gets amplified and all the static and noise gets filtered out. Then comes the magic step. An analog to digital converter, or ADC, takes that nice clean wave and chops it into digital steps. And only then can a computer finally read it and make sense of it all. And here it is. You can see that entire journey in one shot. Just follow it from left to right. You start with the smooth, real-world signal. The sensor turns it into a noisy electrical one. After conditioning, it's a perfect, clean wave. Then it gets digitized into those blocky steps. And finally, it's turned into the ones and zeros the computer understands.
This is it. This is the pipeline that turns our messy analog world into clean, organized data. So let's look at a really powerful example. Remember that EEG cap from the beginning? Each one of those little electrodes is a sensor, picking up those incredibly faint brainwaves. Those signals are then cleaned up, amplified, and digitized, letting doctors literally see a person's brain activity in real time. It's that entire data acquisition process at work, and it saves lives. And it is definitely not just in medicine. These exact same principles are the bedrock of all modern industry. Instead of an EEG, just imagine thousands of sensors in a factory measuring temperature, pressure, and position. They all feed signals into these rugged industrial computers called PLCs. They're the brains of the operation, controlling everything from robot arms on an assembly line to the entire HVAC system in a giant skyscraper. But here's the catch, and this is really, really important. This invisible language we rely on is incredibly powerful. But you know what? It's also incredibly fragile. The messages it carries can break. At the end of the day, a signal is just a carrier for information. And just like any message, it can get garbled by noise, corrupted by interference, or in the absolute worst case scenario, completely wiped out by some kind of overwhelming electrical event. Two of the biggest villains here are ESD and EOS. So think of ESD, electrostatic discharge, as a tiny, super fast lightning strike. It's like that little static shock you get when you touch a doorknob. It's super high voltage, but very low energy. Now, EOS, or electrical overstress, that's a different beast entirely. That's like hooking up a fire hose of electricity to a device and just leaving it on. It's the high energy that does the real lasting damage. And the result is, well, it's what you see right here. This isn't just a glitch that you can reboot. This is catastrophic permanent failure. This microchip didn't just stop working. It was physically blown apart by an electrical event it just couldn't handle. The message wasn't just lost, the messenger was basically vaporized. In the world of engineering, this is what's known as an unrecoverable failure. The hardware is physically destroyed. There is no fixing it, there's no rebooting. The system and any information it was carrying is just gone, forever. So when you really think about it, from the neurons firing inside our own brains to the automated world we've built all around us, everything depends on this elegant but incredibly fragile language. It's this invisible river of information that shapes our reality. And knowing just how easily that message can be shattered, it makes you wonder, are we listening carefully enough?